mathematics. Networks are everywhere in social media, in citation graphs, in emails, in communications, and even in biological systems. To analyze them, we need to identify important nodes. In my classroom lecture, I have told you about why we need to learn about network measures and something about centrality and some metrics and measures. And we also went through some concepts of degree centrality. So the problem with degree centrality is that the centrality is measured on basis of the number of neighbors that a node has. The higher the number of neighbors, the higher the centrality. But this is not always true, meaning if you have more number of friends, it doesn't always mean that you are an influential person, right? Having more number of friends doesn't guarantee you that the person is important. So this is the problem with degree centrality. So how do you overcome this problem of degree centrality? There is another approach called eigenvector centrality, and that's what we are going to discuss now. So this eigenvector centrality generalizes the degree centrality by looking into my neighbors, by which it analyzes, are my neighbors important? Are they connected to considerable number of people? Eigenvector centrality takes into consideration my neighbors. So it states that a node is important if it is connected to other important nodes. Importance flows recursively. So in social networks, your prestige depends not only on how many friends you have, but also on those friends. So in undirected graphs, coming back to graphs, we will take into account all the neighbors of the nodes. So let's assume that eigenvector centrality of a node Ci of Vi. For node Vi, the centrality is Ce, that is eigenvector centrality Ce of Vi. So when my neighbors are important, right? So when my neighbors are important, my importance is also increased. So this is what is the assumption of eigenvector centrality. So what we want is, we want Ce of Vi to be higher than important neighbors, right? If Vj is my neighbor and if Vj is important, then my importance also should be increased. So for incoming neighbors, we will have to assume that Aj is equal to 1. So how do we formulate this example? The assumption that we have made in the centrality of centrality is, this is proportional to the centrality of my neighbors. My centrality is proportional to the neighbors. So the centrality score of a node is proportional to the sum of the centrality of its neighbors. In matrix language, this becomes the eigenvector equation. So the solution is the eigenvector associated with the largest eigenvalue of the adjacency matrix. So since I knew or I assume that it is proportional, I will give it a summation bound with some constant called as lambda. So Ce of Vi, that is centrality of node Vi, will be equal to 1 upon lambda summation of j equals 1 to Aj centrality Ce of Vj. So centrality of Vi will be equal to 1 by lambda times of all the centrality of its neighbors. So if I assume that centrality is a vector matrix like this, given over here, then I can give the formula lambda Ce is equal to At of Ce, where At is adjacency matrix here. So this means that C is an eigenvector of adjacency matrix At and lambda is its corresponding eigenvalue. Now the question arises, which eigenvalue and eigenpair should we choose? Got it? So to answer this question, we have Perrin-Frobnoy's theorem, which says that for all positive real number matrix, there is a matrix of n cross n, and if all the values in the matrix are all positive, then there exists eigenvector and eigenvalue, which is given by lambda max. Okay? So, this lambda max, that is the highest eigenvector, will be chosen as our eigenvector and eigenvalue. So, how do we compute eigenvector centrality of matrix adjacency matrix AJ? So, first we compute the eigenvalues of A, and we will select the largest eigenvalue lambda among all the calculated eigenvalues. And then we will find the corresponding eigenvector of lambda, which we will store in CE. That will be our initial centrality. And based on Perrin-Febvre's theorem, all components of CE will be positive. So these components of CE will be eigenvector centralities for the graph. Got it? So some examples. Consider the three users in a small Instagram network. User A connected to B and C, while B and C are not directly connected. Okay, as given over here. Eigenvector centrality will assign A the highest value, since A links between both sides B, but B and C will have equal centrality, but they will have less than A. Think of LinkedIn. A person connected to CEOs and leaders will have a higher eigenvector centrality than a person connected to hundreds of random accounts. The quality of connections matters more than the count. Let us see the example here. We have a graph with 3 nodes. Its adjacency matrix looks like this. And then we have the formula to calculate eigenvector centrality, which is given by lambda CE is equal to ACE. We will assume that CE is equal to U1, U2, U3, and then let us just put some values in the formula. So if you rewrite the formula, this is how it will look like. And then we will find the determinant of this matrix. We will find the determinant. I hope you know how to calculate the determinant of the matrix. It's simple high school math. So we get this equation. So with this equation, we will calculate, we will get the eigenvalues as minus square root of 2, 2 as 0 and plus square root of 2. So based on the theorem, we will take the highest lambda value here, which is square root of 2. So we will replace this largest eigenvalue in the formula, and this is how it looks like. You can see here. So with this eigenvalue, the centralities that we have got is 1 by 2, root 2 by 2 and 1 by 2. So you can see the vector. So node V1 and V3 has the centrality values. Let us look at another example. So our lambda values here are 2.68, minus 1.74, minus 1.27, 0.33 and 0.00, and we have to choose the highest eigenvalue here, which is 2.68. So with this largest lambda value, we have got the centralities as shown here. To ensure positivity of centrality values, we use the highest eigenvalue. The Perrin-Febvre's theorem guarantees that for matrices with positive entries, the principal eigenvector has positive components. Some applications I can think of, this is like take Twitter influencers. It identifies not only celebrities but also those whose followers themselves are influential. Take in citation networks. A paper cited by highly cited papers is more influential in disease or epidemiology. A person connected to well-connected persons or individuals spreads disease faster. So in corporate emails, employees linked by key managers are structurally more important. So we can keep on giving examples in our day-to-day lives. So the problem with degree centrality was it was directly assuming that if a person has more number of friends, it means that he has more highest importance. But that is not true. So the importance of a person increases as his neighbor is important. This is the assumption that we are making in eigenvector centrality. So the centrality of the node is proportional to the centrality of its neighbors. This is the whole story or summarization of the eigenvector centrality. So now, is this fine? Is there any problems with this? So let's see. The major problem with this eigenvector centrality is when it deals with directed graphs. So the centrality is only passed to the outgoing edges, right? This is problematic in networks like citation networks or hierarchical organizations. Only when there are outgoing edges, these centrality is passed to its neighbors. And in some special cases, when node is a direct acyclic graph, centrality becomes zero even though many edges are connected to it. So this problem has to be handled. Okay. So now comes a new measure. So this problem is handled by cat centrality, K-A-T-Z, cat centrality, by adding an extra term which is beta, which we will call as bias term. In the same eigenvector formula, we will add an extra term which is called as the bias term. So this is how it handles the problem which is occurring in eigenvector centrality. See, the formula is same as eigenvector centrality. The only additional term that we are adding is that bias term. So we have two extra terms here. There is alpha, which is a parameter, which we call it as a controlling term, and we have beta, which is bias term in this new upper measure called cat centrality. So we will rewrite this equation in a vector form. So beta 1, where 1 is beta 1, where 1 is a vector of all the ones, and cat centrality formula looks like this now. So C cards of Vi is given by alpha summation of j equals 1 to n for all neighbors of Vi. Aj is the adjacency matrix and C cards of Vj plus beta, which is bias term. So when alpha is 0, the eigenvector centrality is removed and all the neighbors will get the centrality value beta. The formula states centrality of a node I equals alpha times the sum of neighbors centrality plus beta. So if alpha is 0, everyone has centrality equal to beta. If beta is close to 1 by lambda max, that maximum lambda, then cat centrality approaches eigenvector centrality. So as alpha gets larger, the effect of beta is also reduced. So in practice, we select alpha such that alpha is the largest eigenvalue of adjacent matrix. Got it? So let me give you some examples. Let's take Twitter. Imagine a new user with just one follower, and that follower is Elon Musk. Okay? So degree centrality is very low. Eigenvector centrality may fail if structure is acyclic. But cat centrality assigns a baseline beta plus the strong influence from Elon Musk. So this new user has significant cat centrality. In case of YouTube, a YouTube channel with only 10 subscribers, by the way, subscribe to my channel, with only 10 subscribers, but those subscribers are highly engaged with major creators. Cat centrality accounts for that, giving the new channel importance in recommendation systems. Regarding this formula itself, tuning alpha and beta, alpha controls the weight of longer walks, and smaller the alpha, Cat centrality looks similar to degree centrality. Large alpha, but still less than 1 by lambda maximum, cat centrality approximates to eigenvector centrality. Beta provides the baseline importance, preventing nodes from dropping to 0. So here we have an example. Eigenvectors of this particular adjacency matrix is minus 1.68, minus 1.0, minus 1.0, 0.35 and 3.32. Since 3.32 is the highest value that we have, we will take 1 upon 3.32 as our alpha value, and let us assume our beta value is 0.2, our bias term value is 0.2. So with this we get the scarce centrality value by computing. So these are the values we get for all the nodes. V1 gets the value of 1.14, V2 gets the value 1.31, V3 1.31, V4 1.14 and so on. So V3 are the most important nodes in the graph, V2 and V3. Degree centrality is simply very naive. Eigenvector considers neighbors, that is quality of neighbors and influences. Cats extends eigenvector, ensures non-zero scores, model influence through walks, and so Cats is better in handling some inconsistencies and kind of things that happen in real-time networks. So there are another couple of few measures we will see in our coming lecture.